Hello Algebra 1 students, to graphs of linear functions, and I decided at the last minute to actually finish off this title with etc., and other stuff, which is essentially what etc. means, including intercepts, zeros, what makes a function linear, writing a function rule, and graphing a function rule. So we're going to just do it's a kind of a hodgepodge, kind of a potpourri, if you will, of a bunch of different stuff having to do with linear functions. Let's start. Okay, first of all, there are two basic types of functions that we cover in Algebra 1. Linear functions. A linear function is one whose graph is a non-vertical line. And the reason it has to be non-vertical is that when you're talking about a vertical line, so if we're talking about, say, this vertical line right here, a vertical line cannot be a function. A vertical line cannot be a function because it can't pass the vertical line test if it is a vertical line. So it has to be non-vertical. The other kind of function that we cover in Algebra 1 is quadratic. And that's one whose graph is a parabola. Parabola, let's write that. Parabola. So it's not parabola, that sounds like a disease. A parabola. A parabola is a U-shaped graph. It looks something like that. One way that you can remember that quadratic functions have a U-shaped graph is to look at that U right there in quadratic. So that's good vocabulary for later in the year. Quadratic functions have that parabola, that parabolic graph. Okay, so those are the two basic types of functions. From here on out today, we're going to focus on linear ones. Okay, zeros and intercepts. So all functions can have zeros and intercepts. Let's define them. The x-intercept, there's two intercepts, x and y. The x-intercept of a function is the point where the graph of the function crosses the x-axis. So it's a point where the x value has a number, but the y value does not. It has a 0. So n comma 0, and that n could be a positive or a negative depending on the number we're talking about. The y-intercept of a function is the point where the graph of the function crosses the y-axis. And that means that you'd have 0 for your x and some number for your y. And again, that could be negative or positive. The zeros of a function are the x values at which the y value of the function is equal to 0. So the zeros are actually the same thing as the y value is equal to 0, x-intercepts. So zeros is actually just another name for x-intercepts. We'll use the term zeros more as we move along with functions in this course. What makes a function linear? Well, the first thing that makes a function linear is that the graph of it is a line, okay? So let's put that up here. Its graph, hold on, that's not an apostrophe S, that's just ITS because it's possessive. Its graph is a line. That's the first way we know that a function is linear. But you're not always going to be able to tell what the graph looks like initially. You may have to do something with it first to figure that out. So what else can we use to tell if a function is linear? Well, the equation contains both x and y, or at least y. And remember that f of x and y are interchangeable, and that should have had a closed parentheses there. Oops. Okay, and the other way, so it contains both x and y, or at least y. And remember that f of x is the same thing as y. They're interchangeable. And the other thing is that the x and or the y each have an exponent of 1, albeit invisible. So you can't have x squared or anything else like that. Okay. The other random things we might have, and we'll see that in the examples, cannot be in there if it's going to be linear. Okay. So, are these functions linear? So we're going to use what we've learned so far to determine yes or no whether or not these functions are linear. So, f of x equals x. So if we're saying that's the same as y equals x, it has both x and y. They both have an invisible exponent of 1. And this would indeed give me a straight line if I was to graph points that would go in it. So yes, this one is linear. All right, 3x minus 8. Same thing as y equals 3x minus 8. So it has both x and y. They're both to the first degree. And this, if you recall from last year, has a beginning point on the graph. That's called the y-intercept. So that negative 8 is actually the y-intercept. And we'll cover that more in a later video. And it has what's called a slope. And this gives the steepness of the line. And we'll also cover that in a later video. So this would indeed, if I made a table of ordered pairs, this would indeed give me a line on the coordinate plane. So this one is also linear. Very quickly we can see y equals x cubed. That 3 is not a 1. Automatically not linear. A cubic function does have an interesting shape though. A cubic function like this one does something like that. So that's kind of cool. Okay, this next one is a little bit tricky on my part. I kind of cheated here and gave you one that's a little bit tougher. Because right now you think, oh, totally, they definitely both have an exponent of 1. They do not. They do not. This x right here actually has an exponent on it. And if we rewrote it without putting that in the denominator, it has an exponent of -1. And that right there tells me that no, this is not linear. Okay, that function has a very distinct shape. It's going to look something like this. It's kind of a weird, crazy graph. And the biggest thing I want you to think about here is that x can't be 0, and that's why you see this funky shape, because this function can't touch 0 there. Okay, how about this next one? The absolute value of x. Well, I'm going to tell you a trick on this one. The absolute value of x, just like we had that goofy little trick for quadratic, absolute value graphs make a V-shaped graph, and that is not linear. So having an absolute value in there prevents that from being linear. So no, not linear. All right, and then one last one, y equals -2/3 of x. Well, if we plug in x values and out come the y values, it is going to make a straight line. And we have a degree of 1 on both the x and the y. So yes, this one is indeed linear. We'll get more practice with this as we go along. Plus, we're going to do some fun stuff with our TI-84 graphing calculators with regard to this. So that's it for whether or not these are linear. Let's move on with writing a function rule. So we're going to write a function rule from a word problem. A taxi company charges $4.25 plus $1.50 per mile for rides in the city. Write a function rule for the total rate R as a function of the number of miles M. Use the rule to find the cost of a 6-mile trip. Okay, so a function rule for the total rate R, so R equals, because the total rate equals something having to do with the number of miles. Well, what is it? Well, you start off with $4.25 on the meter plus $1.50 per mile. And if M is the number of miles, we have learned to write the M multiplying the per number, $1.50 per. Sorry, I'm struggling with my decimal points today. They're very messy. There we go, that's better. So there is my function rule. $4.25 plus $1.50 per mile, which means multiplication there. Now we're going to use our function rule to find the cost of a 6-mile trip. So that means I take $4.25 and I add $1.50 times 6. So I'm going to use my calculator because when I'm trying to multitask and make a video, that can be actually really hard. So $1.50 times 6 is $9 plus $4.25, I believe, be $13.25. So that taxi ride costs $13.25. Gosh, that's expensive for 6 miles, isn't it? It's a good thing there's Uber around. Okay, now you try. So I'm going to read it, and then I want you to pause it and try to answer with the function rule. Olaf can make 6 snowballs every minute, but Anna is throwing 3 of them each minute. Write a function rule for the number of snowballs n that they have after m minutes. Then use the rule to find the number of snowballs they have after 30 minutes. Okay, pause it and try. So again, number of snowballs n equals something having to do with the number of minutes, right? So Olaf can make 6 snowballs every minute. So he can make 6 times m snowballs, for m minutes. 6 per minute, 6m. But Anna is throwing 3 of them each minute. So every minute that goes by, she's throwing 3 of them. Now that's not a bad function rule, but let's think about this real quick. Actually, 6m minus 3m, I can do that. This ends up being n equals 3m. And we can go in and just plug right in our 30 minutes. And even with Anna throwing half of them, after 6 minutes, they have made 90 snowballs. Then they just need Elf to come in and throw them really fast. But that crosses over movies, and that's the whole fourth wall breaking down, so we'll pretend I didn't say that. All right. Graphing a function rule is as simple as making a table. You are not going to have to make a table of values for long. You're also going to find that your TI-84 graphing calculator does some of this stuff for you. But we are going to do a few together. So let's go ahead and take a look at this example. The function rule is y equals negative 2x plus 1. Remember that it could just as easily have said f of x equals negative 2x plus 1. And to graph that function rule, someone chose some x values. Now this is the part where you get to decide what your x values are, but you want to think conveniently. If they give you a specific sized graph, then use the graph they gave you because that's where you want to fit your answer. If they didn't give you a specific sized graph, look at the numbers in the function. It wouldn't make sense for me to plug in negative 80 because it's going to give me a really large number that's not going to fit on my graph, and it's just not a convenient number for me to use to tell if I've got this function rule right later on when I'm, if I'm using a calculator or comparing with one another. So they just chose numbers close to 0 and including 0. Notice the use of at least a negative and some positives. They plug those numbers in, find the y values, graph the points, draw a line, bam, done. So let's graph the function rule that we see here, y equals 1/2 x minus 1. So let's graph it. Our function rule was y equals 1/2 x, 1/2, there we go, minus 1. So our table has x in the first column, the function rule in the second column, and then the ordered pair xy in the third column. And that's how that one was set up on the previous slide, I think, basically. So let's figure out what x values we're going to plug in. Now this time, again, we want to be convenient here. I don't want to graph fractions, mostly because I am lazy. I would like to be able to graph on these nice grid lines. See these nice grid lines? I don't want to graph in the middle. I don't want to graph halfway. I want to graph on points that I've got. So what kind of x values do I need to choose? Stop and think. Hopefully someone out there in Cyberland said, oh, I know, evens. Negative 2, 0, 2, 4, and let's also do 6, which fits on my graph. Okay? Now go through and plug in those x values and find the y value. So negative 1/2 times negative 2, so negative half, a half of a negative 2, negative 1, minus 1 is negative 2. Plug in 0. 1/2 of 0 is 0, minus 1 is negative 1, so 0, negative 1. Half of 2 is 1, minus 1 is 0, so 2, 0. Oops, sorry. Random writing because I'm trying to use one of those handwriting bars. I don't think you can see it when I'm actually making the video though. All right, half of 4 is 2, minus 1 is 1, so 4, 1. Half of 6 is 3, minus 1 is 2, so 6, 2. All right, let's plot those over here on our lovely little graph. And I will use, I'll use purple. Orange and purple were my favorite colors as a little kid. All right, so negative 2, did it again. Go away, random writing. Negative 2, negative 2. There we go. 0, negative 1. Points that are on the axes, think carefully when you're graphing. 0 means I don't go left or right, just go down to negative 1. So 0, negative 1. 2, 0. So 2. Don't go up or down, 0, right there. 4, 1, and 6, 2. And I know I did this right because I know, based on what I've learned, that this is a linear function rule. X to the first degree, y to the first degree, they're both there. And I now have a lovely line that I can draw, or a lovely set of points I can draw a line through. Now look, you can see 2 more points we did not choose. Right here, negative 6, negative 4, and right here, negative 4, negative 3. So those are a couple of things to think about when you're graphing a function rule. Now you won't have to make a whole lot of tables like this because pretty soon that graphing calculator will be used to do a lot of that for you. I hope you guys enjoyed. See you in class.